Okay, so the technology is going to prove challenging this year. So actually, while we were on the break, for some reason, my computer disconnected from the internet and I was recording the lecture via Zoom. I mean, I don't need to, I could just record it on the computer, but I want to record via Zoom just to have them in the same format, because in future weeks, I'm going to also have the lecture relaying, broadcasting on Zoom, at least that's the idea. But during the break, there was some internet problem and everything went out and so Zoom disconnected, and then it's, so the video that I paused has now been processed because Zoom crashed. And so that video is complete. So there are going to be 2 videos for this lecture, but I can just imagine there are going, and there are also noises from outside. But anyway, hopefully the technology will become easier as we go along, or at least I'll become more used to it. Right, I just want to give a few more examples of problems and then do the mathematical material, cover the mathematical material I want to cover, which is reminding you, hopefully, I mean, doesn't matter if you haven't seen it before, telling you what big O notation is, but probably many of you have seen that. Then I'll say a little bit about the literature that I'm going to be using for the course, textbooks, and then that will be it for today. So I actually have a long list of examples, but I'm not going to go through them all. I think the next algorithmic problem I want to discuss is something that's useful in various circumstances, which is answering the question whether a graph, in the sense of mathematics, like a graph, like a network of vertices and edges, can be colored in with K colors so that no 2 adjacent vertices have the same color. So does a given graph have a K coloring? I'll use the English, UK English spelling of coloring that has a U there. In American texts, there's no U in coloring. So here the input is a graph, and the question is, can the input is a graph together with a number K, let's say 3, and the question is, can we color the graph with that number of colors so that no 2 adjacent vertices have the coloring in common? So we've got graph coloring. So for example, does the following graph have a 3 coloring? Does the graph have a 3 coloring? Or a K coloring in general, where you input the number K. But let's have a look at the question of the 3 coloring. So suppose we have this graph with 4 vertices and diagonal here. We'll use white as a color. And we can see that this does indeed have a 3 coloring, because obviously these 2 need to be colored differently. There's an edge between them, and then that's okay. These can be white, they need to be different from those. But that does have a 3 coloring. But if we had another edge here, then there's no possible 3 coloring here, because every vertex, this is the clique on 4 vertices, every vertex is connected to every other vertex. And so if we already use 3 colors for 3 vertices, we don't have a color left for this one. So in this case, in the case of this graph, the answer is no. And for those of you who know something about the field of computational complexity, you may know that this question about three colorings is a question that we do not know whether or not we have an efficient algorithm for it. So this is a problem in a very important class that of algorithmic problems called the NP-complete classes. This is going to be a major subject of study at the first part of this course. So this is what's called an NP-complete problem. It's going to take us 2 more lectures to define what this means and to understand it. And for such problems, it is believed that no efficient algorithm exists, but it's an open question whether that's really true. So nobody's been able to prove that. And you may know there is actually a $1 million prize on this question. So if someone can answer this question, you get $1 million. So there is no known efficient algorithm. And it was a very good question. What do we mean by efficient? Because one of the early parts of the course, we're going to give a technical definition, mathematical definition of efficient, but then there is a big discourse that one can have about how really well this corresponds to actual efficiency in practice. There's no known efficient algorithm for answering this question, and it is widely conjectured that none exists, but we don't know how to prove that. It's widely conjectured. So we now, on our list here, for the first one, we found a clever, efficient algorithm. For the second one, I told you that there is a clever, efficient algorithm that involves randomness. And in fact, there's also now known an algorithm without randomness. In the third case, there seems to be a clever, efficient algorithm if we can build a quantum computer. But for answering the question on graph coloring, even a quantum computer is not going to help. It is believed. So this is an apparently hard, it might not look a very difficult problem, but it's an apparently harder problem than the other ones. But also this problem, this question raises another dimension that we might look at, in that for this problem, there are other questions one can ask, not just does a 3 coloring exist, but there are other natural related questions. So we have several related questions. So the first one is the question we were looking at. Given a graph and given a k, a number k, does the graph have a k coloring? So does a k coloring exist? This is called the decision problem. We're deciding yes, no, does the coloring exist? So the decision problem. Does a k coloring exist? You can imagine in practice, in some practical situation that you're looking for a coloring, there are combinatorial situations in which it's useful to know that. You can imagine in practice, you don't just want, it's not that useful to know, yes, one exists if you're not given one. So quite often in practice, you would expect to actually want, instead of a yes answer, you want to actually get a k coloring back as the answer. This is called the search problem, because you're searching actually for a specific k coloring that will color the graph. So there's the search problem. That's find a k coloring, or say no if one doesn't exist. And there's a third problem here that one might be interested in, which is not just does a k-coloring exist or find one, but how many different k-colorings are there? So count the number of k-colorings. So there's also the counting problem. How many k-colorings are there?
What was it about the cases where it's different to count from returning all of them? Right. So there's a counting problem, and then there's the enumeration problem, where you have to like return every k-coloring. Because sometimes you could.
Right. So yeah, they could. So I won't put the enumeration problem down, but indeed there would also be an enumeration problem, which is return a list of all the k-colorings. But in practice, these are questions that we can hope we might get an efficient answer to, because here the answer is yes, no, so it's 1 bit. Here the answer is finding a k-coloring, so that's basically a color assigned to every vertex of the graph, so it's the same size as the graph. Here's the counting problem, how many k-colorings are there? That's a number. The number of k-colorings is going to be, in general, exponential in the size of the graph, but the representation of the number is okay because that's logarithmic in the exponential number of colorings, so that's still something we can get an efficient answer to. But to have an enumeration of all the k-colorings, one would get a list of exponentially many k-colorings, and that's not something we could even hope we would ever want to look at in some sense. So these are somehow the efficient questions, the potentially efficient questions to look at. The second one is clearly at least as hard as the first one, and also the third one is clearly at least as hard as the first one, because from the counting problem you either get 0 or a non-zero number. So the second and third both subsume the first one. But I just wanted to say that there are different kinds of questions one is interested in. Let's just look at one final example. Going back kind of in a circle, back to something related to the determinant, there's a closely related concept called the permanent of an n times n matrix. I'll just take the photo. Out of interest, has anybody in this room heard of the permanent of a matrix? Oh, maybe. That's, I guess, the sort of thing you might cover in discrete maths courses or graph theory courses. It's
one of the possible topics for Račuska and Olga.
Oh, right. Okay. Did you choose it?
No.
No. So the permanent of a matrix. So I wish I got the matrix back on the board, but so we've got, I won't put in, well, let's put in just a few. So here we've got a n1 to a nn. So again, we're with a square matrix. Well, maybe I'll put this in. So again, we've got a square matrix. So remember the Leibniz formula for the determinant that we looked at earlier was over every permutation, so we sum over all permutations on the numbers 1 to n. We sum the sign of the permutation times the product from I equals 1 to n of the entry in row I at column sigma I. Together with, so I missed out the sign of the permutation here, but to get the determinant, we need the sign of the permutation here. The permanent is this formula where you miss out the sign of the permutation. So this is the permanent of A, the same formula that you have for the determinant, but without the sign of the permutation involved. Okay. So what's that good for? So one thing it's good for is there's a situation in which, well, you're interested in pairing two groups of things with each other. So the standard way one would talk about this is boys and girls. You might have n boys. So here's n boys. Just be dots. And here are n girls. This is all very traditional, this way of explaining it, but anyway, let's be traditional for now. We've got n girls here, and there's some set of connections between them. If there's a connection, it means they could tolerate each other or something. Or you might want to be more positive, they like each other. You might have one person connected to more than one. So, and in this situation, there's something called a perfect matching, which is a pairing of boys with girls, so that every boy is paired with exactly one girl and every girl is paired with exactly one boy. A bijection, an explicit bijection between the n girls and the n boys, so that they all tolerate each other, or all like each other. So a perfect matching is a pairing of boys with girls respecting the blue lines, respecting so the idea, in a very traditional setting, you might be wanting to marry the n boys with the n girls and find a way of doing that that's acceptable to the participants. So what's this got to do with the permanent? Well, the blue lines here can be represented by an n by n matrix, where we have, say, boys as the indexes for the row, for indices, I should say, that's the right plural of index. Boys as the indices of the rows, girls as the indices of the columns, and a 1 whenever there's a blue line and a 0 whenever there's not a blue line. So this can be represented. This can be represented by a matrix, an n by n matrix, actually an n by n matrix of zeros and ones. And the permanent in this case of this matrix, is the number of perfect matchings. So it's a solution to a counting problem. Viewed in this way, it's counting the number. So again, for finding perfect matchings, we've got the does there exist a perfect matching? That's the decision problem. Find an explicit perfect matching. That's the practical problem. Can we actually find an appropriate pairing of the boys with the girls? So that's the search problem. And there's the counting problem. And the permanent, this formula is the answer to the counting problem. So permanent of A, in this case, is the number of perfect matchings. So this makes sense whenever you can view the permanent of a matrix as the number of perfect matchings whenever the matrix is a 0-1 matrix. If it's a more general weighted matrix, then it's kind of the sum of weights of perfect matchings for some sets. But let's leave it at this. Number of perfect matchings. So this makes sense when A is a 0-1 matrix. So I'm just trying to give you some idea that permanent is an interesting number. And in this case, so computing the permanent, or let's say looking at perfect matchings. So actually for perfect matchings, the decision problem and the search problem both have efficient solutions. And they're quite elegant solutions. There's a very beautiful algorithm for solving the search problem, find the perfect matching. A very beautiful, efficient algorithm. But the counting problem, which is basically computing the permanent, again, it's an open question whether there is a solution to it. So here we've got an example. Well, sorry, it's an open question whether there's an efficient solution. So although the formula is very similar to the formula for the determinant, and for the formula of the determinant, we were able to find an efficient solution. Omitting this sign information here turns this from a tractable problem, one that we can solve efficiently, to an intractable problem. So again, it is an open question whether permanent of A can be computed efficiently. But again, it's conjectured that it can't be. Okay, and all these open questions.
Is it also?
Right, so very good question. So, I mean, my notes, I was going to put a lot more, but I realized that. So this is worse than NP complete. So I should have said with the k-coloring problem, so that has an efficient solution if and only if P equals NP. So this is the very famous open question in mathematics. It was $1 million prize for, does P equal NP? The k-coloring problem has a solution if and only if P equals NP. The permanent of an n times n matrix has an efficient solution if and only if something called FP equals something called sharp P. And that is, if those two are equal, that implies that P equals NP, but that P could equal NP without those two being equal. So it's somehow, it's more plausible, even though it's very unlikely that k-coloring plus an efficient algorithm for it, it's more plausible that that does than the permanent is efficient. So there are lots of technical definitions being kept out of sight here, but this is the first lecture. And part of what we're going to do on the course is understand the technical picture behind these different levels of difficulty here. Okay, so Are there any questions on that? I think that's enough examples. Yes?
Can like analogous ways to think about this for the determinant?
Well, that's a good question. So for the determinant, we could factorize the matrix this way. Yeah, if nicely using Gaussian elimination, we factorize the matrix and then we compute the determinant of the factors in a very easy way. And that way we get a nice calculation of the determinant. Nobody knows how to do something similar for the permanent. I mean, the permanent doesn't even enjoy a multiplication rule in the second. But nobody knows. There may be clever ways of doing it. People just don't know it. But we think no, because it's this is sort of these problems are kind of getting harder as we go down. Right at the bottom of the list. If you want to find an efficient solution to this, you might as well start on the easier problem of proving that P equals NP. That's easier. Yeah. Any other questions? Okay, so we'll do. So it's actually the way I want to do things. We've had one break, and it's now 10 to 10. But I think there's not that much I want to say. So I think we'll do the technical bit now, and then want to say a little bit about the literature for the course, and then give you a pointer to the video that's for the remaining time. Because the remaining thing to do this week is to watch the video that I'm going to recommend. So I want to do it without another break, but we're going to finish very early, if that's all right. It's also useful not to finish on the hour because my guess is the bottlenecks at the entrances are easier at other times than during the actual hour between the usual lecture finish time.
It's not like any lecture in the hour.
Sorry?
It's not like any actual lecture.
Right, okay. So it's all, yeah, anyway, I'm aiming to finish about 12:30. Let me just take a photo of this. Okay, so when we were talking about the determinant at the beginning, I said that if we explicitly computed the Leibniz formula, the number of multiplications involved would be n factorial times n minus 1, at least if one does it in the most naive way. So there's an explicit formula for if we're computing that algorithm in a sense for how difficult the algorithm is in terms of the number of multiplications. That's not a total measure of how difficult that algorithm is because it also involves a sum. So you multiply numbers and adding numbers. So one might also count the number of additions. And one could, again, have a very precise formula for the number of, say, additions and multiplications involved. But in general, if we're looking at an algorithm, algorithms are not going to just involve additions and multiplications. And anyway, are additions and multiplications themselves basic steps? Or do they take a different amount of time? You might know that multiplication is in general a little bit harder to do than addition, so it takes a little bit longer than addition. There's a question. How are we going to measure how long a computation takes and what's the appropriate mechanism, mathematical mechanism for doing so? And there's the very first thing to do. I want to move away a little bit from looking at precise formulas saying this computation involves n factorial times n minus 1 multiplications, because we're not really that concerned with exactly how many multiplications there are. It's really, if we want to know if an algorithm is efficient or not, we want to know, as we give it harder and harder tasks, or larger and larger tasks, how is the algorithm going to behave with respect to the increase in size of the input we're giving it. So if you have an algorithm that just takes a number of steps proportional to the input size, that's kind of obviously going to be very, very efficient, because you have to give it the input anyway, and if it's only taking a number of steps that's proportional to it, that's kind of, you're in a quite good situation. Another algorithm might go quadratically in the number of inputs, that's in the square of the number of inputs. Another algorithm, like finding a determinant, might grow in the cube of the size of the input. Another algorithms, like the permanent, one implements it naively, permanent, or the determinant, if one implements it naively, will grow sort of super exponentially in the size of the input. And the point is, it's mathematically fruitful, rather than looking at precise functions which are very, very specific to the exactly how you write the algorithm. If you're looking at the precise number of operations, you change the algorithm a little bit and you'll get a different precise function. But you're not going to be able to do any interesting mathematics with that. So rather than looking at precise values of functions in computational complexity theory, we use a way of assessing the rate of growth of a function by looking at what's called its asymptotic rate of growth. And this is this notation that I was using involving big O. There's a related notation involving little o. So this is going to be crucial technical material now. Rather than looking at the precise values of functions, like the precise amount of time a computation is taking, we're going to look at how its rate, the rate of growth of the function. And to do that, we use this notion of this asymptotic growth. And this is you know, I may be a native English speaker, but I don't make it for that. Thank you. So, in COVID times, I also confuse asymptotic with asymptomatic. Although these are both ways of measuring asymptotic growth, but this is, let's call this dominance little o notation. We'll come to it in a moment. The big O notation is really going to be the most important. And the point is, we've got a specific time function a very specific function T of n, something like this. So this is the computation. The T of n, I won't write it down, but it's the computation takes T of n steps to a more mathematically natural function, natural function f of n. So these are functions. In this course, these are going to be functions on the natural numbers, which will include 0. So 0, 1, 2, 3, and so on. And the idea of the O notation is that the O notation will say, apart from small inputs, T of n is eventually dominated by some constant multiple of f of n. So let's give the definition. And so we say T of n. The notation's horrible because this equality is really saying that well, let me actually talk you through it in a moment. This is really saying the function t belongs to the class of functions big O of f, where f is a function. But the n isn't playing any role, except it's only reminding us that t and f are functions. That's the only role played by n here. And it's not a fixed number, it's a variable. But it's the function t belongs to the class of functions that are big O of f. And the equals here, well, it's really membership. T, the function t belongs to this class of functions. But just the standard notation is to use an equals there. So we will stick the standard notation, but it's a bad notation. We say this if there exists a natural number n greater than or equal to 0 and a c greater than or equal to 0 such that for all inputs little n greater than or equal to big N and no, then it holds that T of n is less than or equal to C times F of n. So the point of big N is, apart from on some initial period, which is the numbers up to and including n, apart from the numbers apart from the numbers smaller than n, it holds that the function t is below a constant multiple of f of n. It makes no difference here whether or not we say c can be a real number or an integer or a natural number. Because if we allow c to range over real numbers, we can always just take a bigger natural number. So we could just restrict c to natural numbers, but sometimes it's convenient to use a real number for the constant. So we'll allow, we don't need to, but we will allow c to be a real number. And the nice thing about this notation is it kind of grades functions into a hierarchy. So any linear function, the exercise class is going to be about this notation. But any linear function, so a linear function will be ax plus b for some numbers, coefficients a and b. So any linear function t, for any linear function t, we have t of n is big O of n, because the constants can be absorbed into the big N and the little c. So any linear function is eventually dominated by some constant multiple of the identity function. Any cubic function, for example, there's quadratic in between, just so you know the English. So linear quadratic is n squared, the cubic is with an n cubed. I'm missing out quadratic. For any cubic function, we'll have Tn is O n cubed. And basically one gets a sort of hierarchy of functions like O log n. That's functions that are O log n. If it's logarithmically, asymptotically logarithmic, those are dominated by, those are contained in all the linear ones. So linear ones grow more quickly than logarithmic ones. These grow more quickly than, so quadratic ones grow more quickly than linear ones. And all these, they're all contained in big O of, say, e to the n, so an exponential function. The important thing is this notation allows us to forget, to abstract away from the precise constants in our function. So what the coefficients are in the linear function, and just say this is a linear function or a cubic function, just by looking at the most simple linear and cubic functions. Okay. So how many of you have met big O notation before? Okay, absolutely everyone. Did everyone? Yeah, good. And how many of you have met little O notation before? Okay, not so many. I mean, almost everyone, but so the big O notation is sort of eventually dominated by the problem is I lack the right phrase for describing little O. Let's call it strict dominance or something. So this is big O. That's a good idea. Thank you very much. Goodness me, it's like being at the dentist here with this, without the pain. Let's put the big O notation allows you to say T of n grows at either more slowly or at the same rate as f of n. So, for example, a linear function will grow at the same rate as O of n, at the same rate as the identity function n. Little O notation says T of n grows strictly more slowly than f of n. So f of n really shoots up faster than T of n. So it's strictly dominated by f of n. So to say that, so for the little O notation, we'll change, put the changes in blue. So T of n is little O of f of n. That's a good one. Little O of f of n. Again, if from some point onwards, but actually it needs to be the quantification needs to be the other round. Instead of the c is greater than 0, what we want is that rather than T of n is below some multiple of f of n, We want T of n to be below every multiple of f, eventually below every multiple of f of n. So for that, it's crucial that we have real number multipliers. So it's if for every epsilon greater than 0, where this is, it's now very important that epsilon is a real number. Well, it could be a rational, could be any rational number, that would be enough. But anyway, we'll say a real number. It's important that it's not just integers. For every epsilon greater than 0, there exists an n greater than 0 such that for all numbers bigger than or equal to n, T of n is below epsilon times f of n. So now we have for any linear function, we have that T of n is not below f of n. Sorry, it's not below, it's not little o of n, because little o of n we can use the identity function, we can use a small multiplier, and T of n will not be below it. But it will be, so we have, in this case, we don't have, so we have the T of n is strictly dominated by, for example, n squared. This is little o. Writing on the board, it's very important. I have to be very careful to distinguish big and little o. It's also dominated by n log n, for example. But not T of n is little o. Okay. But the point is, with big O, we've got an upper bound for the rate of growth that it can be growing at the same rate of the function T of n. That's with big O. With little o, the rate of growth has to be growing strictly faster than T of n. That's the idea. So for any, however small real multiplier, we're going to be eventually below the function f of n. Okay, is that clear? Are there any questions about that?
So then the point is that we can compare how three algorithms are like below one algorithm is smaller than below another, then you can actually say that the first one is faster than the second one. If I understand correctly. I'm just curious, why do we have two different notations?
So if T of n is little o of T prime of n, so T prime is the second algorithm, then what we know is that this asymptotically, this algorithm is strictly more efficient than this one. Okay, because eventually this function very much dominates this one. So however much you try to reduce this function by a constant factor, you'll always eventually get above TF. Okay. Whereas the big O, they can be comparable. Yeah. But the exercise class this week is going to look at these notations in more detail, do exercises that cover those. Okay. So I think to end, I just want to give you some literature pointers and then mention the video that I would like you to watch, which is, I mean, we've kind of run into the seminar time a little bit as it is. So I'm sorry that things are going a bit more slowly today, but anyway, I'm going to send you I'm going to point you in the direction of a video that I would like you to watch before next week's lecture. And before that, I'll talk about the literature for the course. And I really hope that next week we're not going to have this sound, as it seems really frustrating. I mean, it would be okay. Normally we could close the windows, but we're not. But we're supposed. I mean, it's also right that we should be ventilating the room. So let's take that. Right. So. So textbooks for the course. So I'm not really going to be specifically following a textbook, but all the material we cover is going to be contained in one textbook that I shall now recommend. But some of the material I will cover in my own way, not exactly in the same way that the textbook covers it. But nonetheless, it's a very good reference to look at for presentation of all the material in the course, and there are several copies in the FMF library of this book. So the main textbook, and all material in the course, although my presentation will be my own in some cases, but the material in the course will be contained in. It's a very, very comprehensive book. So it has a lot of other material. It's a graduate textbook. So this is called Computational Complexity and Modern Approach. A modern approach. And that's by S. Aurora and E. Oh, I can't read my own writing here. I should know it as well, but well, I shall put it on the web page. It begins with B. Anyway, so this is recommended as a mathematical source for looking at, and particularly when you do your seminar presentations, this is going to be a good source for those. Sorry? Bara. How do you spell that? B-A-R-A-K. Oh, right, okay, that's consistent with what's on my sheet of paper. That's good, thank you very much. So if you want a more, so this is a mathematical textbook aimed at graduate students, where this is a master's course. So the level's okay, but it doesn't have a lot of chit chat in. So you want something with a bit more explanation that goes through more slowly, but it will not cover, does not contain all the material in the course. There's book by Michael Tipser. And I think this book is called Computability and Complexity, but I'm not sure. So I should also So I shall put these references on the course webpage. So this is all material and more, much more. This is some course material. It's particularly the initial course material at the start of the course, presented very well. It's really very, very good exposition in this book, presented very clearly. And the third book I want to recommend is not a textbook. It's somewhere between a popular science book and a textbook. I've never seen a book like it, really. It's called Mathematics and Computation. A theory revolutionizing technology and science. And this is by Avi Wittgenstein. So it's almost like a popular science book about computational complexity, only it's a popular science book aimed at a mathematically literate readership. So it's not popular science for you know, in the sense of the average bookshop readership or something like that. So it's popular science ideal for us, let's say. So let's put popular science in quotes, popular science. And another good thing about this book is it's free to download online. It's a book from this year, but you can download it. You can also buy a copy if you want to. And if you like having books on your computer, it's free to download. What's nice about this book is it's setting up computational complexity theory, presenting the main results in an approachable way without the technical details, but you need to know some maths to understand what's being said. Presenting it in such a way that motivating, I mean, I think he almost goes to a little bit to an extreme, but he motivates how important it is to the world we live in. I mean, he views it as a fundamental subject that underpins basically the whole of science and technology. So it's very interesting to read from that perspective. And the author, Avi Wittgenstein, he's been one of the big contributors to computational complexity over the last 30 years. This year, he was awarded the Abel Prize in Mathematics, which, as you may know, that mathematics does not have a Nobel Prize, but then it has a couple of prizes that are a bit like the Nobel Prize. One is the Fields Medal, but the Fields Medal is unlike the Nobel Prize in that it's only awarded every 4 years, although it goes to several different people when it's awarded, but it's also only awarded to mathematicians under 40 years old. The Nobel Prize is more like a prize for specific achievements, irrespective of what age the recipient is. The Abel Prize is a more recently established prize, established, I suppose, about 14 years ago or something like that. It's more like the Nobel Prize in that it's for specific major contributions to mathematics, irrespective of age. And so this year, for the first time, he was one of the recipients, but it's the first time that this mathematics prize has gone to a computer scientist. So this is like a mathematical establishment now recognizing that computer science and computational complexity in particular this guy's work, Avi Vigdisson, is a major contribution to mathematics. And that brings us to the last thing I want to say, which is the video I would like to recommend to you. So this is a video to watch before next week. It's on YouTube. And it is, in fact, by Avi Vigdisson. I'll put a link on the course webpage. And it's called something like the P equals NP question. And it was lectures given, some prize lectures he gave a few years ago at ETH in Zurich. So that should be enough information for you to find it, but as I say, I'll put a link on the course webpage. It's about an hour long, but this is it's a talk for a general audience, but a general scientifically literate audience about this important question, which is going to be a major topic for the first part of this course. Right, I shall stop the recording.